don't touch the camera. Ooh.
I also, because so many of you did not bring your book, but a lot of people took off, so they're missing out again. They're bad. Okay. Here are
Can we get extra credit for
uh,
those who got their
your thing. You're gonna get a copy of the tea table. Let me actually get one for myself. You're gonna get a copy of the tea table, which exists in the back of your book. For those of you who didn't bring your book, and this is for you to keep and bring it to the quiz. And things like that, okay? So this is, so try not to forget these, okay? All right. So we will move on here, okay? No, another smiley face.
That was
I hope everybody's happy with their life, okay?
Take it to the end. If you don't know, then you can. Okay, so what we gonna do? So you're gonna come Sunday night, right?
All right, so moving on, let's do a hypothesis test.
Okay, tell her this. Oh, she left one.
Okay, hypothesis tests. One sample. And we're dealing with a mean. All right, so when you do a hypothesis test, you have to create a pair of hypotheses, right?
let's go.
So we're going to have a null hypothesis
An alternative.
and an alternative hypothesis. So in a hypothesis test that's about the mean, what symbol are we going to have in the null hypothesis? Mu. That's right. Okay. And in this case, a null hypothesis always has an equal sign, and we only have one sample, so there's only one mu. If we're dealing with two samples, we'll have two mu's, right? When we did hypothesis test for proportions, when there was one sample, there was one p.
Right.
When there are two samples, we have two p's. Okay? So one sample hypothesis test mean, we're dealing with mu. Okay? And then you say mu equals what? Okay? You put in some number here. Whatever number is described in the problem, you put that number here. So let's say we say mu is equal to 70. And then the alternative is that mu is maybe not equal to 70. Okay? That's our alternative. Then your data, okay, so depending on the problem, your data may say something like this, okay? So when we're dealing with a sample of data for a mean, what are the what numbers are we going to have? What summary statistics will we have? Okay, so you could think back when we were talking about females in the United States. We had an X bar, we had an S, and there was also an N. Okay, the same type of information exists here. Okay, so let's say someone claims. Let's say we want to do a hypothesis test. Someone says, I believe the average height, or not even this, yeah, someone just says, the average height of women in the United States is 70 inches, okay, 5'10". Well, we gathered a random sample of 10 women, and we got an X bar and an S, and such. Do we have evidence for or against this, okay? So let's say the claim is the average height of women in US is 70 inches, okay? So our data data, and I'm just going to provide the summary numbers that we had from earlier, okay? Our data is from a sample of 10 random women. Okay? Again, quote, but we'll just treat this as a random sample. Okay, so we have n equals 10, my x bar 65.2, and my s 2.6583. Okay, so this is my data. So we want to calculate a p-value, all right? What is the definition of a p-value again? The p-value is the probability of observing your data or something more extreme if the null hypothesis were true. So what this is saying is, you know, for argument's sake, let's say that the average height of women truly was 70 inches. If that were the case, what's the probability that a random sample of 10 women gives me an average height of 65.2 inches? That's what we want to know. 65.2 or something further away from this mean. So in this case, I've got something, this is actually called a t-distribution. So when you're dealing with means, it looks like the normal distribution, but it's actually the t-distribution. And in the center, what number would I put in the center here? 70, the value in my null hypothesis, 70, okay? So this says every time I take a random sample of women, I expect the average to be close to the mean of 70, or whatever this null hypothesis states. Because, right, we're assuming that the null hypothesis is true. Then we want to know if the null hypothesis were actually true, I observed something way over here at 65.2. What's the probability of getting a random sample that gives me 65.2? Alright, is this okay?
Mm-hmm.
So I'm going to get something pretty much, it's a z-score, but because it's the t-distribution, we're going to get a t-score, okay? So think of it just like a z-score, but for t-distribution, a t-score, how would I calculate this?
You go into
Yeah, I would do x bar minus the mean over the standard error, right? Okay, so I would do 65.2 minus the mean of 70 divided by my standard error. Do you guys remember how to get the standard error?
you go into the square root.
S divided by the square root of n. S divided by the square root of n.
This is 65.2.
Oh, I'm sorry, 65.2. Thank you. Didn't mean to cause anyone panic. Okay. 2.6583 over the square root of 10. And I get a standard error, I think, of 0.8406. So far, so good? Okay. Alright, so I have 65.2 minus 70 over 0.8406, and I get a big number. .71. 5.7102. Does that look okay? Oh yeah, negative. Negative 5.7102. Thank you. Is this okay? Okay. Did everyone get a table? One of these T tables? And then did the extras end up somewhere? If I could just have you just bring them forward here, yeah. Okay, so let's we'll take a. So we'll put this on hold. Okay, my t-score is negative 5.7102. Okay, we're gonna put this on hold, and we're gonna learn how to use this t-table. Okay, you already learned how to use it to look up critical values, right? So just quick practice. If I told you make a 90% confidence interval, and your sample had 18 people in it, what is the critical value that you would use in a confidence interval? So your sample has. So if you had 18 people and 90% confidence, you would use 17 degrees of freedom, and you would use 1.740. Everyone's good?
Yes.
If your sample had 18 people, and I asked for a 90% confidence interval, what is the critical value you would use? You would use 17 degrees of freedom, 90% confidence, and your net value is 1.740.
3, 4.
18 people, right? How many degrees of freedom do you have?
7.
N minus 1, 17 degrees of freedom, okay? 18 people, 17 degrees of freedom, so you're going to use 1.74. Yes? Yeah, okay. If you have some different number, let's say 57 people. If you had 57 people, how many degrees of freedom do you have?
56.
56. Do you have 56 degrees of freedom in your table?
No.
No.
No, okay? Anytime you can't find your exact degrees of freedom, always round down. Round down. So you have 56 degrees of freedom, use 50 degrees of freedom, okay?
Oh, round down.
Yeah, round down. Don't round to the nearest, round down, okay? Yeah, so if you have 60 people, you would have 59 degrees of freedom, use
Then you round down.
50 degrees of freedom, okay? I know it feels weird, but it's a rule to be cautious, okay? Yes?
But you will always tell us like the degree of freedom.
No, I will not tell you the degrees of freedom. I will always at least give you a sample size or a way to calculate the sample size, right? So in this case, you can count your sample size, 10, okay? So the sample size will always be provided to you. But from there, you can get degrees of freedom. You just subtract 1, okay? So I think that's okay, right? We can all subtract 1. All right, so let's try that out. So if you have, let's say, 76 people, and I'm asking for a 99% confidence interval, what is the critical value used? 76 people, 99% confidence.
99%.
2.660. 2.660.
Right.
Okay. All right. Do you notice anything about that row infinity degrees of freedom?
Yeah, right.
Anything special about it? No.
It's
It's the numbers you use for your z's, right? They're your z's. 95%, 1.96. 90%, 1.645.
Oh, that's true.
80%, 1.28. You guys see that?
Yes.
Okay. So at infinity degrees of freedom, the t-distribution lines up with the z-scores. Okay, but that's beside the point. All right, let's learn how to use this table. Alright, so please pay attention carefully, because this is very important that we understand how to use this. Okay, so the first thing when you use this t-table is you got to figure out your degrees of freedom, and that's the only row that matters, okay? You figure out your degrees of freedom, that's the only row that matters. So let's say in this problem I have 10 people. How many degrees of freedom do I have?
9.
9, okay? So I'm going to just copy from the table the row with 9 degrees of freedom. Okay, I've got 1.383, and then what I'm going to copy is the row that says right tail probabilities, not the confidence levels. Okay, so it says t.100. Okay, and then t.050 is 1.833, and then 0.025 is 2.262. 0.010.
Where is it?
Okay, and they all have T's in front of them, but that's what we've got. All right, is this okay? That matches what you have in your table. Okay, so this is, the t-table is very different from your normal table. It's very different from everything else. Well, I don't know about very different, but this is how it works, okay? This says, okay, so in the center, I'm going to put the number 0, okay? The mean is 0. And what this says is if I've got 9 degrees of freedom, and if I draw a line, so okay, so you figure a number line, whatever. If I draw a cutoff line at 1.383, okay, at 1.383, and I shaded everything to the right over here, the amount that's in this tail is going to be 10%. Okay, so if I draw a cutoff line at this value, 1.383, the amount that's in the tail, what they say the right tail, that's why it says right tail probability, the amount that's over here is 10%. Does that make sense? Okay. All right. So if I go further away from 0 to 1.833, okay, so 0 is over here, 1.383. If I go further away to 1.833, so here I'm at 1.38, now I'm at 1.83, I'm going to have less in the tail, right? The amount that's further out here, I'm going to have less. And so how much do I have in the tail now? 5%, okay, 0.05. Is that okay? And then if I go even further away to 2.262, the amount that I have in this part is 0.025. Is that okay with everyone? Yes. Okay. So those of you who are visual, this picks up very quickly. Some of you guys are not visual learners, and so it's a little bit tougher to picture what's going on. All right, but that's okay. We're all a little bit different. Okay, but that explains why these numbers get bigger, but the top numbers get smaller. Okay, so one of the common questions is, why are these numbers getting smaller, but these ones are getting bigger? Okay, the reason why is because you're getting further away from 0, so the amount that's left in the tail gets smaller and smaller and smaller. Yes?
So when it's 0.100, is it from that very first hash on the left all the way to the end, or is it just the first hash to the next hash?
No, first hash all the way to the end. Okay, so you're starting here and you're just everything to the right. Okay, and then if I draw a line here and I go everything to the right, it's 0.05. If I draw a line here and I get everything to the right, it's 0.025. Okay, so right here, everything to the right. Is that okay? Okay, so if let's say I draw a line not at 1.383 and not at 1.833, but let's say I draw a line at 1.6. So 1.6 is in between here and here, right? And I ask how much is in the tail beyond 1.6?
We round down to
7.75.
3 minus 1.33 and take a fraction.
No? Okay. All right. So there's all sorts of stuff, okay? Yeah, we could try to interpolate some answer using some algebra. Some of you guys might want to do that. But all we have to say is that if I draw a line at 1.6, the amount that's in my tail, okay, I know for sure is more than what?
It's more than
It's
0.
more than 5%.
Right.
Okay, and the amount in my tail is also for sure what? Less than 10%. Okay? Alright, and I can combine both of these, alright, and some of you guys, the first time you see this, it feels weird, but I'm going to write 10% is greater than my tail, which is greater than 5%, 0.05. Okay? So if I draw a line at 1.6, the amount in my tail I know is less than 10%, but more than 5%. And that's what we are saying, we're writing. Is that concept okay? Is anyone confused? Alright. Okay, because this is an important concept, and I hope this form of writing tails and values is okay also. All this is saying is 10% is greater than the tail, which is greater than 5%, or in other words, the tail is between 5 and 10%. Okay? And another way is if I said my t-score, my score is, t-score is 1.6, you can say, where does 1.6 fit in my number line? Okay, so for those of you who more visual learning is not your strong suit, okay, you can say 1.6 fits in between these two numbers. Okay, so 1.6 goes in between these two numbers, which means my tail area goes in between the corresponding columns. Okay, so 1.6 is between 1.3 and 1.8. Therefore, my tail is between 10 and 5%, okay? So we know that my tail is between these two numbers. Is that okay? All right. What if I said we want to draw a line not at 1.6 or 1.3. Let's say I draw a line at 0.75. Okay? I know my picture's getting all messed up. Okay, so I said if I draw a cutoff at 1.383, the amount in my tail is 10%. What if I'm drawing a cutoff line at 0.75?
Just said it's more than 10%.
Yeah, the amount in my tail
It's greater than 10%.
is greater than 10%. That's exactly right. Okay? I mean, technically we could say it's less than a half because we know it's more than 0, but at that point it doesn't really matter. Okay? Our tail is bigger than 10%. Is that okay? Yeah, okay, all right. And then on the other side, let's say the value I get is 6. All right? Oops.
Like ours is a high, right? Or large.
Yeah. So in our, so the furthest we have written in our table is saying if I draw a line at 3.250, it goes all the way for 9 degrees of freedom, 4.297, right? 4.297 is 0.001. Okay. So the furthest value I have on my table is 4.297. Okay? And that says I've got 0.001. Let's say I draw a line out at 6. How much do I have in my tail?
Less than
Yeah, so the amount in my tail is less than 0.001. Okay? I don't know exactly how much, but I do know that it's less than 0.001. Okay? But again, the the important thing is you figure out your degrees of freedom to lock in that row, okay?
Oh, I
So
see.
you got to figure, because you got so many different rows here, figure out your degrees of freedom, and that's the only row that matters anymore, okay? Once you figure that out, then it's just, if I draw a line here, the amount in my tail is here, this much. If I draw a line here, the amount in my tail is this much. Yes?
Can you explain that one more time? That one.
Okay, so according to my table, if I have 9 degrees of freedom, and I draw a line at 4.297, how much do I have in my tail? I have 0.001 exactly in my tail, okay? If I draw a line even further away from 0, at 6, how much am I going to have in my tail?
Less
I
than.
really don't know. I don't know exactly how much, but I do know for sure it's
gonna
less
be
than
less than
0.001,
that.
okay? Okay, so let's just
But then,
try a few practice problems, okay?
And then
Okay.
you can't do it.
Oh, and then here's the other thing. If you have a negative value, the table is symmetric, okay? So if you have a negative value, just ignore the negative and use that number, okay? So just ignore the negative and look it up. Okay, so let's say your sample size is 15 and your t-score is 2.4. Okay, how much is in the tail? And then let's say in another problem, your degrees of freedom is 23 and your t-score is equal to negative 1.2. How much is in the tail?
We already figured that out.
Okay, do we get answers? Alright, so the first one, I got 15 items in my sample and my score is 2.4. How much is in my tail? Okay, so in this case, I have, alright, so I'm just going to do the entire work, 14 degrees of freedom, and I'm looking for 2.4. The two closest numbers are 2.145 and 2.624, right? 2.4 fits in between here and here. This corresponds to a tail of 0.025, and this corresponds to a tail of 0.010. Is that good?
Yeah.
So my tail, whatever it is, I don't know exactly how much it is. I do know for sure it's less than 0.025 and more than 0.010. Okay? Or, you know, alternatively, you can write 0.025 is greater than your tail, which is greater than 0.010. Okay? You should be comfortable with both forms of writing. Okay, it's saying the same thing, as long as your greater thans or less thans or what you learn these with alligator mouths are pointing in the right direction. Okay. Or eating the bigger number, exactly. Okay. Because of my math background, I tend to write this way, where you write smaller numbers to the left and larger numbers to the right. Okay, that's my habit, but both forms are correct. Although this might be, I guess, stylistically, I don't know, more the norm. Okay, degrees of freedom 23, and your t-score is negative 1.2. How much do you have in your tail? More than 10%. More than 10%. Your answer is more than 10%. Okay? Why? Alright, so we look up 23 degrees of freedom, and the very first number we have is 1.319, and the next number is 1.714, and the corresponding is 10% my tail and 5% my tail. Okay. So here, the value I'm looking up is 1.2. Again, I just ignore my negative signs, okay? So even though I got a negative, I just ignore that. 1.2 is on this side of 1.319, right? It's smaller than that. So my corresponding tail has to be over on that side, okay? So on this side, it's going to be greater. So my tail is greater than 10%, okay? Or if you need to draw the picture, draw the picture. Okay, if I draw a cutoff line at 1.319, the amount in my tail is going to be 10%. If I draw a line that's closer to 0 at 1.2, how much will I have in my tail? More than 10%. I don't know exactly how much, but I do know it's more than 10%. Alright? Is that good?
Yes.
We feel okay using this table? Good. Alright, so let's go back to our problem. And we looked up, we did our math, we did x bar minus mu over the standard error, and my t-score is negative 5.7102. Okay? Negative 5.7102. So how much is in my tail?
Less than 1%.
Okay, so how many degrees of freedom do I have? I have 9 degrees of freedom, and my t-score is equal to negative 5.7102, okay? So I look up 9 degrees of freedom, and then the number furthest out is 4.297, and that corresponds to what?
Less than
0.001, so 1/10 of 1%, really, 1/1000th, okay? So my number of 5.71 is beyond 4.29. So the amount in my tail is going to be less than 0.001. If my t-score was exactly 4.297, how much is in my tail? Exactly 0.001, okay? But my number is bigger than that, so whatever my tail is, it's less than 0.001. Is that okay with everyone? Okay, so I'm getting an extreme value, right? I'm very far away. These are similar to z-scores, but I'm basically 5.71 standard errors away from the mean, which is pretty extreme. I've got a tail less than 0.001, right? Okay, but what was my set of hypotheses going back to this problem? My null hypothesis was that mu equals 70. And my alternative is that mu doesn't equal 70, right? So because of that, or actually, we're looking at negative 5.71. I have a two-sided test. Okay, right? Anytime you have a not equal sign, we have a two-sided test. Do you remember that? Okay, so I've got a not equal sign, so I have a two-sided test, which means I want a tail equally distant from 0. So I got negative 5.71 and 5.71. The amount in this tail is less than 0.001, 1/1000. And the amount in this tail is also less than 1/1000. So if I combine the two tails together, how much do I have total? So the total tail area, yeah, so the total area, whatever it might be, is for sure less than 0.002. Yes?
How do we know, like, in the question, will we know when we're supposed to be looking for our alternative hypothesis equals
To be
not
greater than-
70?
We'll talk about this in more detail, I would say, in next week.
Okay.
and the week after, where we're looking for keywords in the problem.
Okay.
Yeah, so that's a good question. Okay, so my total area, or in this case, this is my p-value. My p-value is less than 0.002. So let's say my alpha is 1%, 0.01. How does my p-value compare to alpha? Yeah, my p-value is smaller than alpha, right? So if my p-value is smaller than alpha, what is the conclusion I do? I reject the null. Alright, my null hypothesis was that mu equals 70. So if I've rejected the null, what does this mean? This means I do have evidence. I have evidence. What?
The mean is 7. The average height of women
That the average height of women in the U.S.
is not 70.
Yeah, in the U.S. is not, oops, not 70 inches. I hope this is okay. Alright, we'll cover all of the concepts, and then if we have time we'll do a few examples, but I feel like we've got a good amount to cover. So, okay, so that is hypothesis tests for one sample dealing with means. Okay, so we've done confidence intervals for one sample with means, hypothesis tests for one sample with means. What do you think we're going to do now?
Two means. Two samples.
Confidence intervals and hypothesis tests for two samples and means. Okay. I know, you guys are really excited. Ugh. Okay. Be excited. All right. Confidence intervals, two samples, means. Okay? If we have two samples, we're going to have two x bars, we're going to have two standard deviations, and we're going to have two ends. Okay? So your data, whatever it might be, will summarize. Well, data should have. If you have two samples, you're going to have an N1 and an N2. You're going to have an X bar 1,
X bar 2,
X bar 2, and a standard deviation of 1,
standard
and
deviation.
standard deviation 2. There you go. So you're going to have these values. We're going to use these in our confidence interval. Okay. Confidence interval is always a statement about what? The population, right? It's always a statement about the parameters of the population. So in this case, we're going to look at one sample and another sample, and we're making a statement about the difference between the means in the population. Okay? So for example, let's say sample 1 is men and sample 2 is women. Okay? I could find the average height of men in my sample and the average height of women in my sample. The confidence interval, however, is about the populations, and it's about the difference in average height between men and women. So what's the difference in average height of men and women? So the average height of my sample for men might be like 69.8 inches or something. The average height for women might be 65.2 inches or something. The confidence interval will be about the difference. So it's going to say the difference in average height between a man and a woman is that, I would say, you know, I'm 95% confident that men are between 3 to 6 inches taller than women, or something like that, okay? So the resulting interval is just about the difference in average heights. It's not about, I don't mention anything about how tall a man is and how tall a woman is. I'm just talking about the difference. I'm saying the difference in average heights between men and women, you know, I'm 90% confident is between 3 to 6 inches. So I'm 90% confident that men are between 3 to 6 inches taller, or that the average height of men is between 3 to 6 inches taller than the average height of women. Is that okay? Okay, so it's a statement about the difference, not about the means themselves. It's a statement about the difference between the means. Okay, so we are making difference between means. So that is mu1 minus mu2. Okay, an example would be, you know, I am 90% confident that the average height of males between, we say 3 to 6 inches taller So this is where we are aiming to go. We're looking for the difference between mu1 and mu2. We're making a confidence interval for mu1, difference between mu1 and mu2. Alright. You guys remember, so just recap. Alright. Confidence interval for proportions, for one proportion. We never did confidence interval for two proportions, and we're not going to. What did we do? We put in the middle, what did we put? P hat plus or minus Z star times the standard error. Okay, now we're making a confidence for, again, this is also a review. When we did a confidence interval for one mean, what do we put in the middle? Not T star. Huh? What goes here in the beginning, in the middle? X bar,
X bar.
okay? When I say middle, I'm talking about the middle of the interval, right? Because this forms our center, and we go plus a value, and we go minus a value. So X bar, and then we did plus or minus a T star times a standard error. So now we are making a confidence interval for what? The difference between means, mu1 minus mu2. So what do you think is going to go in this place? What's going to form the center of my interval? What's that? I think I heard it. It's going to be the difference between
M1 and M2.
X bar 1 and X bar 2. Okay? Right? So here basically I'm making an interval about this population parameter, and I put in my estimate for that. This is my population parameter, and this is my best guess for that. Okay, so this goes right in the middle. And then I'm going to go plus or minus T star times standard error. Is that okay? So they're all similar. There's very much a parallelism between all of these. So confidence interval for the difference between means, mu1 minus mu2, as the center is X bar 1 minus X bar 2, plus or minus T star times standard error. Okay. And just like everything else, the standard error, I'm going to just give you an equation or a formula. There's nothing you can do about it. This is just what we're going to use. Okay? This is probably the second ugliest standard error next to the standard error for different two proportions. This one's not too bad. Okay? You take the standard deviation of the first sample, you square it, divide by n1. Take the standard deviation of the second sample, you square it, divide by n2. That's it. It's not too horrible. Easy, easy peasy, right? The worst one is by far the standard error for a difference between two proportions. That is by far the worst.
So would that be standard deviation 3 times?
What do you mean? I only see 2.
Don't you have to do the first one, the second one, and then all of them together?
Wait, what? Sorry.
Isn't standard deviation
This
1?
Wait. What are we talking about? So you find the standard error, standard deviations of the first sample, the standard deviation of the second sample, S1 and S2, okay? So you figure these out, and then you combine them to get this standard error.
Oh, okay.
Okay? Okay. Is that alright? Alright, so let's make a confidence interval. So make one last thing. When you pick your T star, you got to know the confidence level and the degrees of freedom. Okay? So the degrees of freedom for T star is what is still n minus 1. Okay? But you've got 2 n's. Whichever, use the smaller n. Okay? So it's still n minus 1, but use the smaller n. Okay, you've got 2 n's. Just use the smaller n and do n minus 1. Alright, so now, here is your exercise, in-class exercise. Make a, we'll say 90% confidence interval for the difference between the mean height of men and women. Alright, so let's say sample 1 is the men. asked 9 men, and let's say their average height was 69.7 inches, and the standard deviation, let's say, was 2.84. Okay? And then for sample 2, was women, and let's say our N2 was 65.2 inches. I'm sorry, that's not N2. N2, let's say we asked 10 women, and our X bar 2 was 65.2 inches, and our standard deviation, let's say, was 2.84. No, it's the same number. Let's say 2.70. Okay? So with this information, this is your data. Make a 90% confidence interval. Okay? So I'll remove this. The unnecessary part, this is all you need, okay? This, and that. You can Alright? Everybody should be able to do this, okay? Nobody should be staring at the wall or the board with blank stares, okay? All the information you need, this is literally plugging in numbers where they belong and figuring it out, okay? This is easy. The hardest part is using your table to figure out your T-star.
That's actually the easy part.
Is that the easy part? Maybe the hardest part is punching it in your calculator without making a mistake.
How would I put this
Just punch it in exactly as you see it.
so like
You know, whatever the S1, it'd be a square button. So you probably have do you have a square button on your calculator? Cassius generally do. That's your square button. Okay? Divided by n plus button. That's 2 square button. Divided by n2 equals. And then square root button. Cancel button. You got one of these. All right, we ready? Okay. No? One more minute. All right, fine.
What does it say? Don't make error.
All right, how about now? Well, at least we're participating.
Oh no.
Alright, ready or not? Here we go.
Almost.
All we're doing is we're just plugging in numbers here, okay?
Yes, yes.
X bar 1, 69.7. Minus X bar 2, 65.2. Okay? So the center, if I do this, I get 4.5 inches. Okay? Is that alright?
That's right.
Plus or minus a T star times my standard error. Okay? So let's figure out T star. Okay? T star, how many degrees of freedom do I have?
8.
Okay, I use n minus 1, and I'm going to choose the smaller n, so I do 9 minus 1, I've got 8 degrees of freedom. Alright, what is my confidence level? I said make it 90%. Okay, so my T star, 90% confidence, 8 degrees of freedom. T star is 1.860. Okay, so I'm going to just plug in 1.860. Standard error. Okay, yep. We're just going to plug in the numbers that we have into the standard error formula. 2.84 squared over n1, 9, plus 2.70 squared over n2, 10. Alright? Now, some of you guys are asking, how do I punch this into my calculator? I just do 2.84, and then if you have a square button, which looks like x2, you do that, and then you just do divide by 9, plus button. It's going to take forever just for me to write it on the board. Okay, and then you hit the square root button, answer key, equals.
1.275.
Is that what we get?
1.275. Yeah, it's around.
Divided by 9. Here, let's,
How many is it?
I don't know, I like to keep 4, alright? So, so my standard error, when I do all of this, I get 1.2748. It is easy. That's what I've been trying to say. Alright. I've been trying to tell you. Alright. 1.2748. Actually, and then if you just leave it in your calculator, you don't even have to worry about this rounding business. Just leave it in there and do times 1.86, and you get 2.37112 or whatever. Okay. 4.5 plus or minus 2.3712. You don't have to keep that many. All right. 4.5. So on the high end, 4.5 plus 2.37 gives me 6.87 on the high end. I'm rounding out to 2 decimals now. And then 4.5 minus 2.37 gives me 2.13 on the low end. Alright, so my confidence interval goes something like this. I say, I am 90% confident that the average height of men is between 2.13 inches and 6.87 inches taller than women. And that's it. Does this provide evidence that men are taller than women? That the average height of men is taller than the average height of women?
Would we say yes, or would we say that it doesn't not?
This is my
Did
question.
you say prove?
Does it not prove, but does this provide evidence
Yeah.
Yes.
that the average height of men is taller than women? Average height of women.
No.
Mm.
It does not prove.
It does. It does, okay? Because why? Because 0 is not in my interval, right?
Okay.
If there were no difference between the average height of men and women, we would expect to see 0 within my interval. But 0 is not in my interval. I'm confident that the average height of men, at least, at the low end, is 2 inches taller than the average height of women. And at the high end is close to 7 inches taller than women. What's the true average height difference? I don't know. It's probably something around 5.5 inches. But this says that the average height difference is between 2.13 and 6.87. So in this case, because 0 is not within the interval, I have evidence that there is a difference. Alright, so this is a key thing to write down and remember and learn. Because 0 is not in my interval, or is not within, I'll write within my interval, I have evidence that there is a true difference between the population means. So 0 is not within the interval. So we have evidence that there is a true difference between the population means. Okay? If 0 were in the interval, then we would not have evidence of a difference. Yes?
On the quiz, all of this would be given, right? We just need to find the T.
So this part might be given to you. Okay?
Right.
Yeah.
That's what I meant.
Yeah.
Structure.
Yeah. I could give you raw numbers, and you could calculate x bar and standard deviation yourself, right? You could.
Yeah.
It might be tedious and time consuming, and I probably won't do that. But it's not totally unreasonable either, right? Yes?
Is it always 0 or you chose 0 for this problem?
When we're looking for a true difference, it's always going to be 0. Okay? When it was for one sample, we picked the number that we want to look for. So, or I would say, I would ask questions like, do we have evidence that the average height of women is not 70 inches or something? And we're looking for 70 within the confidence interval. But in this case, this is a confidence interval for the difference between the average height of men and women.
So if 0 is not in between, you have evidence?
We do have evidence. Yeah. Alright, is this okay? Good. Alright, so we have one last thing to cover. Alright, I know. This is a long chapter. We'll get through it, okay? And then next week, we'll cover chapter 12, which is a lightweight chapter, okay? It's easy. The homework for chapter 12 is very easy, okay? But next week, we'll also start our final exam review, or just really our reviews of chapters 8 and 9. And the other big part of your homework next week is to work on the practice final exam, okay? I do this because I want you guys to succeed, all right? I give you this work so you learn the stuff, not to make your lives terrible, okay? Honestly, all right? I care, all right? Let's do this last topic. Hypothesis tests for 2 samples, and we're dealing with means, okay? At the very beginning of class, we did a hypothesis test for 2 samples, but it was for proportions. This time we're doing a hypothesis test for 2 samples and we're dealing with means. Alright, so I'll write out a scenario, okay? Alright. We want to know, alright, so let's say some company says we've got this miracle weight loss pill, okay? Every few years, some company does say we've got this miracle weight loss pill, right? Okay, so we want to know if the miracle weight loss pill alright, so what is this? Miracle weight loss pill works. Okay? So basically, for the miracle weight loss pill to work, what we need to see is people who take the pill, what? Lose weight, right? Maybe not a ton of weight, but if everybody who takes the pill loses some weight, I'd say it works, okay? Alright, this is a fictional thing that I'm making up here, okay? So don't get your hopes up if you're looking for a miracle weight loss pill, alright? I need a miracle weight gain pill. Alright, we want to know if this works. Alright, so we're going to compare it to placebo. Alright, group 1, they get the placebo. Gets placebo. So let's say we find 50 volunteers, okay? Alright, let's just say, okay, so group 1 gets the placebo, and let's say 26 are in group 1. And they all take the pill for, I don't know, a month. Okay, so after 1 month, they all lost an average. So let's say the average weight loss is X bar 1. As everybody lost, you know, the average weight loss is 1.4 pounds, okay? With a standard deviation of 1.1 pound. Is that okay?
This one.
Huh? So that's group 1. Group 2 gets miracle weight loss pill. Alright, so how many are in group 2? 24 are in group 2. And let's say after 1 month, X bar 2 is negative 2.9 pounds, okay, with a standard deviation of 1.2 pounds. Okay, so those who took the placebo lost an average of 1.4. Those who took the miracle weight loss pill lost an average of 2.9. Okay, so does this data provide evidence that the miracle weight loss pill is more effective than placebo? We'll say more effective Alright. Yes.
For the S, you put S1 in the
Oh yeah, I gotta put S1 and S2, thank you. Alright, is this okay? The idea behind this, good. Okay, let's get started. Alright, that's the last thing we have to cover, alright? So, be super excited. Alright. This is not how smiley faces work. Smiley faces. Alright, so my null hypothesis, okay? We want to know, is the miracle weight loss pill more effective than the placebo? So my null hypothesis in words would be what? That the weight loss pill and the placebo are equally effective, okay? So is equally effective as placebo. Okay? Or I should say placebo is equally effective as miracle weight loss pill because I've called placebo group 1 and miracle weight loss pill as group 2. Okay? That's just a technicality, but we will okay? Is that alright? So my null hypothesis in symbols would be what?
H-O-N.
I'm making a statement about what? The population mean. So it's going to be that mu1 minus mu2 equals 0. Okay? Alright. And then the alternative is what? Miracle weight loss pill is more effective than placebo, or in other words, placebo is less effective than miracle weight loss pill. Now, this is where you have to think, and things get a little bit tricky, okay? Weight loss is a negative number, right? So, if the placebo is less effective than the miracle weight loss pill, the difference in the weight lost, if I do placebo minus weight loss pill, should that be greater than 0 or less than 0?
Less than 0.
Okay, so the weight change is a negative number though.
Well, because we want placebo.
Alright, so it gets confusing, okay? The answer is that it should be greater than 0. But you can if you're not entirely sure, just write some sample numbers down, okay, to see what happens, okay? So let's say somebody starts off at 150 pounds, and after taking placebo, let's just say it's not that effective, they lose 1 pound, so they end up at 149, so that weight change is what?
-1.
Minus 1. Okay. With the weight loss pill, let's say it was 150, and just give it the benefit of the doubt, because this is the alternative that we want to see if this is what's happening, okay? So if they took the thing, they should have lost, let's say maybe they lost 5 pounds, okay? 145.
Right.
So then their weight change is what?
-5.
-5, okay? So if I do the alternative of mu1 minus mu2, I would do -1 minus a -5. This would be greater than 0.
Right.
Okay? So sometimes if you just try to think about it, you're going to get confused and you're going to pick the wrong one, greater or less than. So sometimes it's best to just use some sample numbers and figure this out.
Right.
Yes?
I have a question. Since you used group 1 as a placebo, does your question have to be different? Does this provide evidence that the weight loss pill is more effective than placebo?
No, I mean, this is the question that we're after. Maybe I should have labeled my groups, group 2 and group 1. It doesn't really matter. As long as we're consistent in what we do here, and then we're able to take our results to answer our original question, we're okay. All right, so we just have to make sure we can answer this original question. All right. So, what is my observed difference? The observed difference in weight losses. Observed difference between average weight change. I know it's a little bit weird, okay? But basically, I'm just going to do x bar 1 minus x bar 2. This is my observed difference. So x bar 1, they lost an average of, or their weight change average was 1.4 pounds down. Okay?